Today we are going to start a new topic, but I think before doing that, it's good to kind of review what we have done so far. Very quick review. So we started this course by studying the kinematics of particles. So kinematics of particles. And then from there, after studying the kinematics of particles in various coordinate systems like curvilinear coordinate systems, cylindrical, spherical, we went to study the kinematics of rigid bodies. So kinematics of rigid bodies. And we had all sort of problems where we had kind of like rotating frame, two rotating frames, a particle moving with respect to a rigid body that itself is just rotating or moving. We had all sort of the problems. So the natural next step for us after this was studying the kinetics, because we were done with the kinematics, and then we actually started the kinetics. So kinetics, but for the particle. So kinetics of particle. And this was basically just Newton's second law. We said that the sum of all the forces that is acting on a particle is equal to ma, mass times its acceleration. And we saw that this is actually very easy because we were able to just calculate the right hand side of this equation, which is a kinematic property, acceleration, from the kinematic sections of this lecture. So this was basically just using the kinematics that we know and just using these vector equations and calculating the force or whatever unknown that we had in the problems. But here, before going to kinetics of the rigid body, so kinematics of the particle, kinematics of rigid bodies, kinetics of particles. Before going to kinetics of rigid bodies, we said that it's good to just learn another approach, which is work and energy, to solve dynamics problems. And we saw how we can use the work and energy principle to study the motion of particles. So here we had work and energy for particles. And also here, we touched on angular momentum and impulse, and we saw a couple of examples of angular momentum. But today, after this, so the next step for us, we studied the kinetics of particle. We saw how we can use work and energy to solve problems on particles. Now we want to go to kinetics of rigid bodies. So today's lecture is going to be about the kinetics of rigid bodies. So kinetics, and few next lecture is going to be about this kinetics of rigid bodies. And here, instead of just saying that here are the equations for a rigid body, we actually want to derive them. And here our discussion would be mainly focused on 2D kinetics. We won't study 3D kinetics in this course, but we will derive the equations of motion for a 2D rigid body object. So let's start that. In order to do this, so we want to our main goal is that to start from this equation, which is for a particle, Newton's second law, and kind of like expand on this to derive some equations for bodies with dimensions, rigid bodies, in 2D. So that is our goal. Using this equation for particle, what can we get for rigid bodies? So let's assume that we have a rigid body in a coordinate system. So here, let's say we have a coordinate system here. So this is y, this is x, and we have a general 2D object here. So this is the object that we want to study its motion. And there are all sort of forces that are acting on this rigid body. So we want to start from particles and get the equation for rigid body. So this rigid body, we can think of it as a bag of particles. just we can think of it as collection of particles that are in this rigid body. This rigid body consists of particles, bunch of particles, infinite number of particles. But for now, let's just say that these are the particles that just comprises this rigid body. So there are all sort of forces that are acting on these particles. So on each particle, we might have an external force that is acting on that particle. So for example, let's say this is particle 1. We show it with dm1. dm1 is just mass of that particle. So let's say this one. And we have an external force that is acting on this particle. So this is F1. And we have, for example, another external force that is acting on this particle. Let's say this is dm2. So this is F2. And I show the external forces with capital F here. So F2 for dm2. And we can just keep going on with this. So we can say that this is the ith particle with dmi, dmi, and we have force Fi, that is an external force acting on this particle. So this would be Fi. So these are for external forces. We also have internal forces between these particles. So each of these particles are just interacting with each other, and we have internal forces between them. So I can show the internal forces with a small letter f. So let's say this is dm1, and we show the internal forces due to all the other particles with f1 as a small f1. So here, let's say this is F1. So this would be the sum of all the internal forces that are acting on particle 1. So let's say particle 2 is exerting a force, influencing particle 1 with some force, particle 3, particle 4, 5, all the way to particle I, and sum of all those forces is just F1. So as F1, external F1. So F1 is the sum of all the external forces that are acting on particle 1. So we might have a couple of forces, external forces that are acting on particle 1, but we sum all of those forces and we show them with F1. So we have the same thing for particle 2, particle I, and so on and so forth. So here is just, for example, let's say this is, oops, this got bad. Let's say this is, my pen is acting up. Okay, so this is, for example, F, oops. Okay, now it's working. Sorry for that. So this is F2. And on particle I, we have, let's say, Fi here. Okay, so now that we have these forces acting on separate particles, let's write down the Newton's second law for particles. So for particle dm1, particle 1, we can write down F1 plus F1, external force acting on particle 1 plus internal forces acting on particle 1 is equal to dm1 a1. And a1 is just the acceleration of particle 1. dm1 is mass of that particle 1. We can do the same thing for particle 2. F2 plus F2 is equal to dm2 A2, and all the way to the ith particle. So here Fi plus Fi is equal to dmi Ai. So these are, as I said, these are the Newton's law for particles. So now that we have the Newton's law written for all particles, let's sum up all the forces here on the left hand sides and also the right hand side terms together. So I can say that, so for all these equations, I can just sum the left hand side together and also the right hand side together. So I can say that sigma Fi, this is the sum of all the external forces that are acting on all the particles, plus sigma Fi is equal to, this is the sum of all the internal forces that are acting on all the particles. It's equal to sigma dmi Ai. So, and the sigma is on I. So we are adding up the left hand sides together and also the right hand sides together. So here's the point. I can say that this term is equal to 0 actually. So the sum of all the internal forces on all the particle is equal to 0. Why? It's easy. It's because of the Newton's third law actually. So this term is equal to 0. To show how this term is 0, so you can think of that. Because we have Newton's third law, so let's say particle 2 is acting force. Let's actually have a rigid body with, for example, 3 particles. So let's say we have a rigid body. Let's say this is particle 1, this is particle 2, this is particle 3. So for these 3 particles, the force that particle 2 is exerting on particle 1, let's just show it with F21. And force that particle 3 is exerting on particle 1, let's show it with F31. Force that is acting from particle 3 on particle 1. But we have the reaction of these forces because of Newton's third law. If particle 2 is exerting F21 on particle 1, particle 1 is also exerting the same force but in the opposite direction on particle 2. So I can say that here we have F12, which is equal to minus F21. And for for force that particle 3 is exerting on particle 1, F31, again the same thing is true. Particle 1 is just exerting the same force in the opposite direction on particle 3. So this wouldn't actually be here. So let me write down over here. So this would be, for example, F. It would be along the same line. Let me write this better. Use a line. Okay, so this is, let's say this is F21. This is, for example, F21. This is F31. So on the same line, we are going to have F13, which is the opposite direction of F31 here, that is acting on particle 3. So this would be F31. And over here we have the same thing. So this would be should be along the same line. So okay, now they are on the same line here. So this is F12, which is actually equal to minus F2, 1. And same thing over here. So this is equal to minus F1, 3. And we can do the forces that is acting from particle 2 on particle 3 to on particle 2. But you get the idea. If we sum up all these forces together, the result would be 0 because we have F31, but we have also minus F31. So this is F13 that is equal to F13 that is equal to minus F31. And over here, this is F12, which is equal to minus F21. So you can see that if we sum up all these forces together, the result would be 0 because for any force we have also is negative, is a negative term that is equal to that force but in the opposite direction. So the sum of all these forces, the sum of all the internal forces, it would be 0. So if this term is equal to 0, then we are left with sigma Fi, which remember that capital Fi is the sum of all the external forces on the rigid body. This would be equal to sigma dm I a I. Okay. Now I can say that, okay, so a rigid body basically is just infinite number of particles. And what's the way that we can turn this summation to include infinite number of particles? Well, we have to turn this into an integral. So this would be the sum of all the external forces. So I would say that F external, sum of all the external forces, and this would turn out into an integral over the rigid body. So this would be A dm, so over rigid body, Okay, so on so good. So now let's see how we can simplify this term. Where in order to just, to write this term in a meaningful way, we have to also remember the definition of center of mass. So for a rigid body, let's say again we have so we leave this equation for now and kind of like go to definition of rigid body, and then we come back to see how we can further simplify this term. So, oops. My pen is not working. There we go, that's not bad. Okay, so for a center of mass definition, so, oops, sorry for this. See if it is working. Nope. Center of mass. So you are all familiar with this concept. So this concept is about if we have a rigid body and this rigid body, as we said, is just consists of a bunch of particles, and we want to just kind of like see where, how the mass is distributed in this rigid body, or we want to see if we were to kind of like model this rigid body with one point, with a particle that has the same mass as a rigid body, where would the location of that particle be? So here, to do that, we would say that the location of center of mass, center of mass here, which we show it with RG, G for here, probably for gravity, I don't know, but if the gravity field is just is uniform, the center of mass would be equal to center of gravity. But if we have a kind of like a gravity field that is changing with location, these two are not necessarily equal to each other. But let's say that we have we are on Earth, we have a uniform gravity field, and we want to calculate the center of mass. We show it with RG. So here we have an XY coordinate again. So this is X, this is Y, and the definition of the location of that point that represents the mass of this rigid body would be kind of like the average of location of all the particles weighted by their mass. So this would be R dm over dm. So for example, for this particle dm1, this is basically, we are saying that R1 dm1. So this is R1. For another particle dm2, we use this vector R2. So if we do this for all the particle, of course, again, it turns out to be an integral, we are going to have this equation. Okay, so we can also simplify this kind of a denominator here. So the integral of dm would be just the mass of rigid body. So this would be 1 over m integral of r dm. Okay. So now for this equation, let's take derivative from both sides with respect to t. So we are going to have drg over dt is going to be 1 over m, which is constant here, and the derivative can go inside the integral, so it would be dr over dt dm. What is this? So this is the definition of velocity. And what is this? This is the velocity of center of mass. So this g would be a point. If we calculate this integral, it would be a point on the rigid body. So let's say this is g. It is not necessarily always on the rigid body. If we have something like this, for example, kind of like a half a ring, the center of mass actually would be would not be on the rigid body. It virtually belongs to the rigid body. But anyway, this point, we can calculate it. It would be a point. And drg over dt, that would be the velocity of that point, velocity of center of mass. So I can write down here, I can say that this is equal to vg is equal to 1 over m integral. This is velocity, so velocity dm. Let's take another derivative from this equation. So we get dvg over dt is equal to 1 over m integral dv over dt m. Again, what is this term? This is the acceleration of center of mass. So this would be a g, and this integral dv over dt, that's the definition of acceleration. So 1 over m integral of acceleration dm. Now we start to see why we are doing this. So this a dm, this is a term that showed up here, integral of a dm. So I can write down here that the integral of a dm is just equal to m times ag. So I can say a dm, this is equal to basically multiplying both sides by m. So m ag. Okay, so this integral is equal to mass of the rigid body times the acceleration of center of mass. So now let's plug in this equation into the previous equation that we had over here. So what do we get? We get the Newton's second law equation for rigid bodies. So we get F external, or sum of all the external forces, is equal to m a g. So basically here we say that the Newton's second law is going to be true, but we have to just account for the acceleration of center of mass. So for a rigid body, we already know that different points on the rigid body can have different velocity and different acceleration. We extensively studied this in the kinematics part of the course, and we calculated the velocity and acceleration of different points on a rigid body. And here we are saying that if you want to write down the Newton's equation for a rigid body, you have to consider the A would be the acceleration of the center of mass. Okay, so this is one equation that we have for rigid body. So this is the first equation. We are going to derive another equation for the rigid body. So this is the first equation for rigid body. So first equation for rigid body. Now let's derive another equation for a rigid body. So again, let's have our rigid body. So let's say again we have our rigid body here. This is y, this is x, and we have a rigid body, 2D rigid body here. And for this rigid body, let's say we have the velocity and acceleration of one point of this rigid body, and we call this point P. And the rigid body is just under general motion, so we are going to have omega and also alpha. If we have the velocity and acceleration of this point P, we already know that we can, and if we also know the omega and alpha, we already know that we can write down the acceleration and velocity of any other point on the rigid body. So let me attach a coordinate system to this rigid body at this point that we have its velocity. So I would say that this is the coordinate system that is attached to this rigid body, and it is just moving and rotating with it. So let me actually show this x and y with capital X and y for the inertial frame. So this is x, this is y. And for the rotating frame, for the moving frame, let's say this is x, this is y. And here, just we have considered this rotating frame in a way that its axis is just parallel to the inertial frame, but that doesn't kind of like affect our procedure, the equation that we want to derive. Okay, so we have this point P on the rigid body. We have its velocity, acceleration. We have omega and alpha, and now I can write down again the Newton's equation for particles, for any particle on this rigid body. So again, let's say we have a bunch of particles here. I just show one of them. I show the forces for one of them, but you get the idea. So here, let's say this is dm1, actually it's better to write it here, dm1. This is the first particle. So for this particle, I can write down its acceleration with respect to acceleration of point P. So from kinematics. So if this is r, the relative position of that point, dm1, with respect to the point that we have its velocity and acceleration. So this would be r1. Okay. What can I say? I can say for dm1 that a1, acceleration of point 1, is equal to ap plus omega cross r plus alpha cross r. We had this in the kinematics section. So this is the acceleration of particle dm1. Again, we have all sort of forces that are acting on this particle. We have external forces here. Let me show it with blue here. Okay, so let's say this is F1, sum of all the forces that are acting on particle 1. And also we have, for example, F2 here, F1, small f, lowercase f1, which is sum of all the forces, internal forces that are acting on particle 1. So for particle 1, I can say that F1, again, this is Newton's second law for a particle. We said that we want to derive all the equations for the rigid body starting from this equation. So F1 plus F1 is equal to dm1 times a1. Okay, but a1 we just wrote down the acceleration of point 1 based on point P. So I can say that F1 plus F1 is equal to dm1 AP plus omega cross r plus alpha cross r. Okay, so now let's actually just simplify these terms. Let's see what we can get from this. So because we are in 2D, for AP I can write down AP is equal to an x component APX, the I direction, plus AP Y in the J direction. So that's for AP. For omega, again, because we are in 2D, omega would be in the direction normal to the plane, so that would be in the z direction. So I can write down omega is equal to omega in the z direction, in the k, and k is just normal in the z direction. And for r, I can write down r is equal to x in the I direction in this coordinate system. So this R1 would be x in the I direction plus y in the j direction. So here when we set r, this is R1 basically. R1. Okay. Now before substituting these quantities into this equation and doing the cross product, I want to do actually one further step here. And that is multiplying both sides of this equation by R1. So I want to say that I want to multiply both sides by R1. So this would be R1 cross F1 plus F1 is equal to dm1. And here we are going to have R1 cross AP plus R cross omega cross R plus R, and again R here is just R1 cross alpha cross R1. Okay, so we just, we can do that. We just multiply both sides of that equation by R1. Now, we can simplify this. So this term R1 cross omega cross R1, this is equal to 0 because basically I can here just switch the order of vectors and just say this is equal to minus omega cross R1. And then we are going to have minus omega cross R1 cross omega cross R1. So we're going to have the cross product of the vector by itself, and that is equal to 0. So we can say that this term is equal to 0. Here my pen is not working. Okay. So this term is equal to 0. this is 0. And for the other terms, now we can just simplify them using these equations that we had. So what do we have? We have R1 cross AP. So let's do the cross product of R1 by AP. So R1 cross AP, let's write it down here with another color. So R1 cross AP. This would be X in the I direction plus Y, J direction, cross product by AP. AP is just APX I plus APY J. So if we do this product, we're going to have I cross I is 0, I cross J is K. So we are going to have X, APY, and here Y cross, J cross I would be minus Y, APX in the K direction. And J cross J is 0. So that's for this term, R cross AP. And let's also calculate this, R cross alpha cross R1. So R1 cross alpha cross R1. So this would be X in the I direction plus Y in the J direction cross alpha in the K direction, X. So alpha, I should write down here also that alpha is also a scalar in the K direction. So alpha K cross Xi plus Yj. And the parenthesis here. Okay. So we can do this product. So this would be basically alpha cross minus this minus x squared in the I direction minus y squared in the j direction. But let's do the cross product. So this would be again x in the I plus y in the j cross over here. K cross I, that would be j, so that would be alpha x j. And k cross j is minus I, so that would be minus alpha y I. Okay, and now let's do the other cross product. So here, this would be x cross, I cross j would be k, so that would be alpha x squared in the k direction. And I cross I is 0, j cross j is 0, j cross I, that is minus k. And we have a minus sign here, so this would be plus alpha y squared k. So this is basically alpha x squared plus y squared in the k direction. Okay, good. So now we calculated all of these terms, R1 cross AP and also R1 cross alpha cross R1. So let's substitute them into the equation. So we are going to have R1 cross F1 plus R1 cross F1 is equal to dm1, and over here we are going to have, so notice that all of these terms are in the k direction, so I can factor out k and I can say that x a p y minus y a p x plus alpha x squared plus y squared, and all of these terms are in the k direction. And this makes sense. So because F1, all the forces are in xy plane, and also R is in the xy plane, so the cross product of these two vectors are going to be normal to both vectors. So the cross product of these vectors are always going to be in the k direction. So that's good that we have just a k component here. Okay, so I wrote down this for particle M1, but we can do the same thing for particle 2, particle 3, and all the way to particle I. So I can actually say that this is true for Ri, So the same thing that we did over there, I want to just write down this equation for all the particles and then sum up the left hand side together and also right hand side together. So here this would be Ri cross Fy plus Ri cross Fi is equal to dmi xi. So this is basically x1, y1, xy, x1, y1, xi a p y minus y1 a p x plus yi actually. So x I squared plus y I squared, and everything is in the k direction. Okay, now that we have written this equation for all the particles for the rigid body. So remember that the rigid body that we had over here, we wrote down the equation for one of them, but we can write down for all the particles. And if we do that and then sum up the left hand side terms together and also right hand side together, we are going to have this. We're going to have sigma Ri cross Fi plus sigma Ri cross Fi. This is equal to sigma xi a py minus yi a px plus x squared. Oh, we had an alpha here. X squared plus y squared alpha, and here everything times dmi, and again everything in the k direction. Okay, so but here is the point again. This term would be equal to 0 because for any internal force that we have, let's say F12, we are going to have also F21 that is just equal to minus F12. So with the same argument that we had when we were deriving the first equation, this term is also equal to 0. So this is equal to 0. Okay, so what do we have? We have Ri cross Fi is equal to this integral over this term over here. Let me see actually if I can copy this. So just save time a little. Okay. So now we have this. But what is this term? So we know that this is the R cross F would be moment of force F. So this is basically the moment, the sum of the moments due to all of the forces, external forces that are acting on the particle. So this would be actually sigma m moment external is equal to this term. And actually let's just go one step further here. So we can turn this sigma into an integral because we are basically having infinite number of particles in the rigid body. So I can write down this like this. So I can say that this is equal to integral x apy dm minus y ap, or actually let's just go one step further also. So here this would be, let's take APY and APX out of the integrals because these are constants, these are just numbers. So this would be APY integral x dm plus a or minus APX y dm. So this whole thing should be in the k direction, plus alpha integral x squared plus y squared dm. And everything is in the k direction. And I actually right now, because we are in 2D, we can I can drop the vector notations, because this is we know that this is in the k direction, this is also in the k direction, so I can just write down the scalar form of this, which is basically the same thing without the vector sign. So this would be sigma, and this sigma external, the sum of all the moments. It's good to notice that this is around P. So that Ri that we were having, so that Ri was measured with respect to the P. The point that we had is at velocity and acceleration. So we should know what point we are taking as a reference when we are calculating the moments. So sigma of all the moments, external moments, around point P is equal to this term. But what are these terms? X dm, integral x dm, y dm, and also this term. So we just had the definition for the center of mass. So remember, for the center of mass we had Rg is equal to R dm over m. If I write down this in terms of the components, so this would be xg, the I direction, plus yg in the j direction is equal to x dm over m in the I direction plus y dm over m, the whole thing over m, in the j direction. So x dm, the integral of x dm would be just m times x of g, because now the I components are equal to each other. So these terms are equal to each other, should be equal to each other, and these terms also should be equal to each other. So x dm, integral of x dm would be just m times x of g, the x coordinate of the center of mass. And also integral of y dm should be m times yg. So I can just use this equation and rewrite these integrals. What about the third integral? Well, we have a definition for this integral. We know that this is second moment of inertia. So remember that, again, we had, not in this course, but I'm sure that you are familiar with this definition, that the second moment of inertia for a body, for a rigid body, would be integral of x squared plus y squared dm. So this is second moment of inertia. So this integral x squared plus y squared dm, I can just show it with I. But again, it is important to know where is the reference point for calculating the moment of inertia. Where is the origin for that calculation? And here we are basically, this x and y are measured with respect to point P. Remember, R was measured with respect to point P, so x1 and y1 will also be the x and y coordinate coordinate of particle dm1 with respect to P. So we need to show here that this is with respect to point P, for example. Okay, we can calculate this integral with respect to any points. We're going to get different values, but here, because we were measuring x and y with respect to P, we have to show that. Okay, now that we have this definition, I can just write down this in a simplified format. So I can say that sigma m external around P is equal to, and actually I said that I'm not going to write down the vector because everything is in the k direction. So sigma sum of all the moment external forces around point P would be APY times, this is mxg. So I can, let me write it this way. Let me say this is mxg APY minus, here APX times, this is MYG. I have factored out M, so this would be YG APX plus, and this is, we said that this is I, so this would be I again with respect to P times alpha. So this is the second equation that we were actually looking for. So let me highlight this. Okay, so this is the second equation. We had the first equation, which was sigma F is equal to MAG, and over here, this is the second equation for a rigid body. Second equation for a rigid body, a 2D rigid body. And the name of this equation is actually Euler equation. So this is Euler equation. Okay, so there are a couple of important points regarding this Euler equation. And that is, you oftentimes see students just write, or anybody write down that sigma m is equal to I alpha. Well, that's not true. You know, we just derived that this is the whole equation. This is the whole, the Euler equation in a full format for a 2D rigid body. So we cannot say that sigma m external in general is equal to I alpha. But there are cases that we can say that. There are cases, special cases that we can say that sum of all the moments is equal to I moment of inertia times alpha. So it would be kind of like a moment version of the Newton's second law. We had F equal MAG, and people like to just say that sigma F is equal to I alpha. So instead of M we have I, instead of F we have moment, and instead of acceleration we have angular acceleration. But again, this is not true for all the points. This equation in general has this term. But there are instances, as I said, that this term is equal to 0, and then we can say that sigma m is equal to IP alpha. So a very, very important point to keep in mind is that sigma m is not always equal to I alpha. There are certain cases that equation is true. Let's see what are those cases. The first case is that special cases. So here we have special cases. We wrote down this equation for an arbitrary point P. This point P wasn't any special point. It was just a random point that we considered, and this was the full Euler equation. But if we don't choose that point, just random, if we consider that point, the first special case, if we consider P, if we consider the center of gravity as the point P that we are deriving all these equations for. So the first special case is that if P, the point that we are taking as a reference, is center of mass. If that's true, if P is equal to G, then basically what we have is that xg is equal to 0 and yg is equal to 0. Because if that's the origin of our coordinate system, if we just put this as g, so what is the position of g within that coordinate? Well, it is in the origin, and the origin is just 0 and 0. So if P is equal to G, then xg, yg equal to 0, then we can simplify this equation. We can say that sigma m external around G here is equal to I G alpha. So for those of you that you like to just have this kind of like a equivalent format of the F equal to MA for rotation, it's just good to keep in mind that this is true if the point is always center of mass. So sigma m equal to IG alpha is true if that point is just center of mass. So we can always keep this in mind. But the problem is that it's not always easy to just consider that G as a reference point. Sometimes you have points for the rigid body that that some of the forces that are passing through that point, and that makes calculating this term easier. If the force is just passing through a point, its moment around that point would be 0. But if that point is not center of mass, we cannot write down this, and we have to use this full format. So it is good to have this, but it's also good to keep in mind that this might not be always the easiest option to choose. Sometimes it is easy to choose another point rather than from the center of mass. So if our arbitrary point is center of mass, this equation is true. That term goes to 0. Another special case that this equation again reduces to m equal to I alpha is that when the acceleration of point P is just equal to 0. So if APX is equal to 0, APY equal to 0, like what? Like a pinpoint for a rigid body. So imagine that you have, for example, a rigid body, a disk that is pinned, for example, at this point. Even if this point wasn't the center of mass, still we can write this m equal to I alpha. So let's say we have a disk that has a kind of like inhomogeneous distribution of mass. So the center of mass, let's say, is here. But the disk is pinned at point O, and the acceleration of that point is 0. So then we can say, go back to this equation and say that this term is equal to 0. So here we can say that sigma m external over O is equal to IO alpha. If O is stationary, its acceleration is 0. Okay, so that's another special case. The third special case, which again, I have never used this third special case, but it's good to know in solving problems. At least the problems that I have dealt with, it's just always either I use this first case or this second special case, or actually just a general format. But it's also good to know that there is another case that this equation just reduces to sigma m is equal to I alpha, and that is when this term is equal to 0. So if xg a py minus yg a px is equal to 0, then we get yg over xg is equal to a py over a px. And what does this mean? This means that if the point that we are considering as a reference point, the P, if its acceleration passes through the center of gravity, center of mass, then again, this equation, the Euler equation, reduces to sigma m is equal to I. So this is P if this equation is equal to 0, IP alpha. So basically we are saying that if we have a rigid body, let's say we have a rigid body, and let's say this is G, center of mass, and we have point P here. So this is our reference point, but the acceleration of point P is just passing through the center of mass. So the acceleration is either in this direction or in this direction, but the important thing is that the line of action for that vector is passing through G. So this is basically, we are saying that this acceleration, so this is A, P, and this is passing through point G. If the acceleration of point passes through the center of mass, again we can just simplify this equation, the Euler equation, and just write down sigma m is equal to I alpha. So I cannot emphasize more than this, that this is very important to keep in mind. If you see a 2D kinetic problem, and the equations that we want to use to solve that problem is just F equal mag, the first equation that we derived, and the second equation is just this equation. And then we have to consider if we want to just choose the reference point as one of these special cases so that we can reduce this equation to sigma m equal to I alpha, or no, if we want to just write down this equation in a general format and just keep these terms here. So sigma m is equal to m xgapy minus ygapx plus ip alpha. So these are the equations that we derived for the kinetics of the rigid bodies, and I think we have time to just solve one example today, and then we keep continuing solving problems in the next lectures. So let me actually write down the question so that we can save some time and just solve one example of the application of these two formulas. Okay, so here we want to solve an example for the kinetics of the rigid bodies. But before doing that, I thought that it's good to kind of like do a quick review on the moment of inertia for some of the shapes that we encounter with them in the problems. So we said that this is the formula that we have for calculating the second moment of inertia. And if we do this integration for example, a rectangle, a homogeneous rectangle. So right now we are assuming that the density of this rectangle is just constant. So if that's the case, then if we do the integration for a rectangle, we're going to come up with m over 12 a squared plus b squared. And this is around the center of mass here, G, which would be for a homogeneous rectangle would be at the center. Again, these are some formulas that you are already familiar with, but to kind of like just review. For a circle, for a homogeneous circle, the moment of inertia around its center of mass, would be 1 over 2m r squared. For a half a circle, we are going to have I over O, which O here is not the center of mass anymore. We know you can calculate this or just refer to tables that where is the center of mass for a semicircle. I think it was like 4r over 3 pi, something like that. But it's not at the center of the semicircle anymore. But if we calculate this moment of inertia, we said that we can calculate it around any point, not just center of mass. If we calculate that around O, that would be 1 over 2m r squared. And m here is just a mass of half a circle. M here is just a mass of full circle. Again, m here is just a mass of this rectangle. For a kind of like a bar or a link that is just it is very long in one dimension and has very short dimension in the other direction, we can kind of like use this formula and just say that okay, A is just approaching L and B is approaching to 0, and we are going to come up with 1 over 12 ml squared. So this is the moment of inertia for a bar, a long bar around its center of mass, which is at the center. So again, these are things that you are familiar with. Another thing that is good to review here is just the parallel axis theorem. And the idea here is that if you have the center of mass, and if we have the moment of inertia around the center of mass, and we want to calculate the moment of inertia around another point, but the point is that the coordinate system, the axis of the coordinate system should be parallel to the coordinate system that we had at the center of mass. That's why we call it the parallel axis theorem. So let's call them, actually these are x prime, y prime. If the coordinate systems have parallel axes at 2 points, one of them is center of mass, by just having the moment of inertia around the center of gravity, center of mass, we can calculate the moment of inertia around the other point by just having the distance between that point and the center of mass. So this is again a very useful formula. For example, for this bar that we had, we might need to calculate the center of mass around one end of this bar, not at the center. And we can just use the parallel axis theorem here. I have written down that if we have this bar here, we know the moment of inertia around this center of mass. If you want to calculate the moment of inertia at A, we just write down IA is equal to IG plus M D squared. D is just distance between A and G, which here is just half the length of the bar here. So that would be L over 2. So IG plus M L over 2 squared. So we're going to have IG was 1 over 12 ML squared plus ML squared over 4. The result is just ML squared over 3. One important note here to keep in mind here is that we can use this theorem when one of the point is the center of mass. So if we have another point here, this is again one of the common mistake. So let's say we have another point here. Let me use a green color here. Let's say we have a point B here. And we have a coordinate system that has a kind of like parallel axis. So let's show the coordinate system. Let's say this is X. This is, let me actually erase this B here. Okay. So let's say these are the axes. Oops. These are the axes at B. So this is, for example, y double prime and x double prime here. The point here is that so this is point B. We cannot write down the parallel axis theorem between these 2 points. We can always write this, we can only write this when one of the points is center of mass. So if we want to kind of like obtain a relationship between this moment of inertia between these 2 points, we have to go from A, we have to go to center of mass and then go to B. So here we have IA is equal to IG plus MT squared. I can also write down IB is equal to IG plus M, and let's call the other distance B squared, for example. So here B would be the distance between point B and G. So that's B. So if you want to just write down the equation between A and B, so I can write down here IG is equal to IB minus M B squared. And now I can just substitute this into the equation for A. So we get IA is equal to IB minus M B squared plus M D squared, which we get IA is equal to IB plus M D squared minus B squared. So if you want to go from A to B, we cannot say just IA is equal to IB plus the distance between these 2 points squared. No, we have to consider the distance from the center of mass, go to the center of mass, and then go to any other point that we want. So again, these are reviews. So with these things in mind, now let's just solve an example here. So very, very simple example. So we have a bar that is just pinned at point A, and it is rotating with the angular velocity of 20 radian per second. The moment of 300 Newton times meter is applied on this bar. the length of the bar is 4 meters, its mass is 20 kilograms, and we are asked to find the acceleration, angular acceleration of the bar, and also the force that is exerted by this pin A on the bar. And we have the gravity in this direction, 10 meters per second square. So definitely this is a kinetic of a rigid body example. We don't have a particle anymore. We have a body, a 2D rigid body with a dimension. We are given the length of the rigid body. So we have to use our formula that we derived for a rigid body. So let's show the free body diagram for this rigid body. That is always our first step, whether we are studying particles or rigid bodies, and then we write down the equation to see what we can get from them. So if I kind of like draw the rigid body here again, so oops. So let's say this is the bar. Okay. So what are the forces that are acting on this bar? Well, we have this external moment that is acting on the bar, so let's just show that. So this is M equal to 300 Newton meter. That's the first external moment that is acting on this. We have the force of gravity that is acting on this, on the center of mass. It's actually acting on the whole rigid body, but we can consider it as a force that is equal to mass of the whole rigid body times the acceleration of gravity at the center of mass for the rigid body. And because we have a homogeneous rigid body here, the center of mass is actually here at the center. So we are going to have force of gravity here. So this would be mg. And also we have the force that is exerted by the pin on the rigid body. So we don't know them. Let's just show it by its components. So we are going to have AX and AY. Unknown component of the pin force. So this is A, and that's A of X, this is A of Y. So this is A, Y, and this is A, X. So these are all the forces that are acting on this rigid body. And now we can go ahead and write down our equation. What are the equations for a rigid body? Well, we have the Newton's equation, which is sigma F is equal to m a g, and we have the Euler equation, which says that sigma m for any arbitrary point is equal to ap alpha plus m xg ap y minus yg ap x. I think I write that down. Yeah, that's correct. So these are the equations that we have. This is Newton, and this is Euler. Let's start from Newton. So from Newton, we can write down that here we have minus mg, we have axi, so we are going to have axi plus ayj minus mg in the minus j direction. That's why we have the minus. Is equal, these are all the forces that are acting on the rigid body. This is equal to m a g, the acceleration of center of mass, which here g is here. Okay, so that's the first equation. For the second equation, here what is the best point that we can consider for this rigid body? So I would say that the best point to calculate the moment of the external forces is just this point A. Why? Well, a couple of reasons. First is that this AX and AY is just passing through this point A, and therefore when we calculate the moment of the external forces, their moment would be equal to 0. So that makes our job easier. The second thing is that because this is a pinpoint, its acceleration is actually equal to 0. So this term would go to 0, and then we have just sigma m is equal to I alpha, which again is easier to deal with compared to this equation. So the point that I consider for the moment, so this should be your kind of like thought process in considering a reference point. If you don't want to use this, and the next easy point would be the G. Why? Because again, this force AX is just passing through this, mg is passing through this, so we have to just calculate the moment of one force. And the second reason is that because we are writing the equations around the center of mass, this term again would go to 0. So I would say this is the first easy point, and after that, if you don't want to consider this, you can consider the center of mass. But you can consider any point. So somebody could just write down the equation from here, I don't know, any point, even if it is not on the rigid body. You can consider it from here, but that makes your kind of like job harder, because then you have to calculate the moment of all these forces. You have to consider the equation in its full format. So I would use point A here. So I would say that sigma A is equal to A alpha, and I just note that A is stationary. So its acceleration AA is equal to 0. That's why I can reduce this equation to this equation. So basically here we have this to this, and also the Newton's equation to this equation. Okay. So far so good. So let's simplify these equations. The acceleration of point G, I can write it down based on point A, again from kinematics. So I can say that AG is equal to AA plus omega cross R. Plus alpha cross R. And R here is just G with respect to A. So G with respect to A. Okay. So what is the acceleration of point A? That's 0. So this is 0. I can say that AG is equal to omega. We have omega. Omega is 20 radian per second. So, and it is in the counterclockwise direction. So if this is our X direction, if this is our Y direction, the Z direction would be out of plane. So this is 20 in the positive K direction. So this would be 20K cross 20K cross RG with respect to A. So here this would be L over 2 in the I direction. And what is L? L is 4 meters. So L over 2 would be 2 meters. So this would be 2 in the I direction. Plus alpha. We don't know the value of alpha. That is one of the things that the question is asking for. So we just put an unknown quantity alpha, but we know it's going to be in the K direction, either positive or negative. So alpha in the K direction cross RG with respect to A. Again, that's L over 2 in the I direction. L is 4, so that would be 2 in the I direction. Okay, this is vector. So we are going to have, this is going to be 20 times 20, 400 times 20, 800, and it would be in the minus I direction. So minus 800 in the I direction. And here K cross I would be J. So this would be plus 2 alpha J. That's the acceleration of point G. Okay, so with this acceleration, let's rewrite this equation again. So we are going to have AX, and I put the I terms together and also J terms together. So AX in the I direction plus AY minus MG in the J direction. So I am just writing down that equation here. It's equal to M, which we have the value of M, by the way. M, I think, is 20 kilogram. Yeah, 20 kilograms. So this would be 20 times minus 800 in the I direction plus 2 alpha in the j direction. Okay, so from this equation we can say that the I terms should be equal to each other and j terms should be equal to each other. So we get AX is equal to 20 times minus 800, so that would be 16,000 minus 16,000, and in the j components also should be equal to each other, so we get AY minus mg. Again, we have m is 20 times g 10, that's going to be 200. Minus 200 is equal to 20 times 2 alpha, so that would be 40 alpha. Okay, so we have 2 equations, but we have 3 unknowns. So 2 equations, 3 unknowns. Alpha, AX, and AY. So we need to use our Euler equation to get the third equation so that we can calculate all of those unknowns. So remember, sigma MA was IA times alpha. So what is I here? For a bar, we just mentioned this, above here. For a bar, around the center of mass, the moment of inertia, where is it? Was 1 over 12 mls squared, but around one of its endpoint would be mls squared over 3. So that's the I of a bar over one of its ends. So here, because we are considering point A, we have to use that mls squared over 3. So we get sigma MA is equal to I, which is 1 over 3 mls squared times alpha, which again alpha is unknown. Let's calculate the moments, the moments that we have on the rigid body. So we are calculating the moments around this point. We have a just pure moment here, so that would be 300, because it is in the counterclockwise direction, so it would be positive 300 K. So we put positive 300 over here, so this would be positive 300. And remember, we said that this equation is just in the K direction, and we drop the vector notation. So if a moment is just in the positive direction K, we just show it with a positive scalar value. If it is in the minus K direction, we show it with a minus scalar value. Here is just the external M is in the positive K direction. That's why we have positive 300 K. So what are the other moments that we have here? Well, these 2 components do not generate any moments around point A. So that's good. And we are only left with mg over here. And the moment of mg around this point would be mg times this length, this arm, which is L over 2, and it would be in the clockwise direction, so it would be in the minus K direction. So we show it with a negative scalar value. So we would say minus mg L over 2 is equal to 1 over 3 m, which is 20 kilogram, times L squared, which is 16 times alpha. This is our third equation. The only unknown in this equation is just alpha. So we got 3 equations, 3 unknowns, and we should be able to solve it. So here, basically, let's solve this. This would be 300 minus m, again, is just 4 times, m was 20, sorry, L is 4. So 20 times 10 times 4 over 2 is equal to 20 times 16, that would be 320 over 3 alpha. So here, this would be 200, 800 over to 400, so that would be minus 100. Is that correct? 200, 800, yes, minus 100 is equal to 320 over 3 alpha. So alpha would be minus 300 over 320. Or you can simplify this, minus 30 over 32. Further simplifying this, let's just divide by 2. That would be minus 15 over 16. And its dimension would be radiant per second square. And we got a negative value for alpha. That means that the alpha should be in this direction, in the clockwise direction. So, and that makes sense. We had this mg terms that is trying to just rotate this bar in this direction, and we had this external force in the other direction. So this acceleration is the moment of this force is kind of like dominating this force, and that's why the acceleration would be, angular acceleration would be in the clockwise direction. So that's for alpha. Alpha is equal to minus 15 over 60. Radiant per second square. For ax and ay, we can just substitute alpha into the equation. Here ax is actually just found. We have ax, it's just minus 16,000. And for ay, we just need to substitute the value of alpha that we got to solve this. So ax is also minus 16,000. So that's ax, and for ay is equal to 40 alpha plus 200. So this would be 40 alpha plus 200. That would be 40 times minus 15 over 16 plus 200. This is, if we simplify by 8, this would be 5 times 15, that would be minus 75. And if we simplify by 8, this would be 2 plus 200. And you can further simplify this. So that's for ay. So using the Newton's equation for a rigid body and also Euler equation for a rigid body, we were able to find the quantities that we were asked in the question, alpha and also the force at the point A. So this is the procedure to solve the kinetics problem for 2D rigid bodies. We have to draw the free body diagram. Sometimes we need to calculate the kinematic properties like we did here. We had to find the acceleration of point G based on point A, because we were just given the angular velocity of the bar, not the angular acceleration, or we didn't have the acceleration of point G. So we had to kind of like come up with an equation with that. We used the kinematics, and just using the free body diagrams, some equations from kinematics, and most importantly the Newton's and Euler equation, we were able to solve this. So this is the theme for the next few lectures, to solve problems on 2D rigid bodies, kinetics of 2D rigid bodies. So I guess, with this, we finish this lecture, and I see you guys in the next lecture.